What if I told you that the most powerful open source AI model ever released is basically a remix? Kimi K2.5 packs a trillion parameters into a mixture of experts architecture, but only activates 32 billion of them per token, and it handles 128,000 tokens of context. That alone would be impressive, but here's where it gets interesting. This model runs on the exact same architecture as DeepSeek V3. Same transformer blocks, same attention mechanism, same expert routing. And somehow it's crushing models that cost 10 times more to use. So the question isn't what did they build, because the answer is nothing new. The question is how did they train it, because that's where everything changes. Let me show you exactly what Moonshot AI figured out. To understand what makes Kimi K2.5 special, you need to see it next to the model it's based on, because when you put them side by side, the differences are surprisingly subtle. DeepSeek V3 comes in at 671 billion parameters, with 128 attention heads, 256 experts, and 37 billion parameters active per token. Its first three transformer blocks run dense feed-forward layers before switching to sparse experts. Now look at Kimi K2.5. It's bigger overall at 1.04 trillion parameters, but it actually uses fewer attention heads, just 64, which is exactly half. It compensates with more experts, 384 of them, which is 50% more than DeepSeek. It activates slightly less per token at 32 billion, and only the very first block runs dense before switching to experts. So when you zoom out, the changes are architectural nudges, not a redesign. Fewer heads, more experts, same vocabulary, same SwiGLU activation, same multi-head latent attention. The architecture is a remix, which means the entire performance gap between these two models comes down to training decisions. And those training decisions are genuinely wild. Since mixture of experts is the backbone of this entire model, let's actually walk through what happens inside it when a token shows up. When a token enters a mixture of experts layer, the first thing it hits is a router, which is a learned gating network that looks at that token's representation and decides which expert should process it. Out of 384 total experts, the router picks 8, and then there's one shared expert that always activates regardless. So 9 experts fire for every single token. Each of those experts is a SwiGLU feed-forward network. The input hits a linear layer that splits into two parallel paths. One passes through a SwiGLU activation and the other goes through a separate linear transformation. Those two paths multiply element-wise, and then a final projection brings everything back together. The intermediate dimension is 2048. Now here's the math that makes this whole thing work. The model has a trillion parameters in total, but because only 9 experts fire per token, you're only using 32 billion parameters in any given forward pass. That's 48x sparsity, meaning you get the knowledge capacity of a trillion parameter model at the computational cost of a 32 billion parameter one. That trade-off is the entire foundation of why this model can compete with the best while costing a fraction to run. Two things make this model actually work at the scale they're pushing it to, and both of them solve problems that would otherwise make training impossible. The first is multi-head latent attention. The core problem is that 128,000 tokens of context means a standard key-value cache would eat your entire GPU memory budget. Multi-head latent attention solves this by compressing key-value pairs into a low-dimensional latent space before caching them. When the input comes in, it gets squeezed down to a compact representation and then decompressed when it's time to compute attention. A standard cache scales linearly with the full hidden dimension, but multi-head latent attention scales with a much smaller compressed dimension, which is how you fit 128,000 tokens in memory without melting your hardware. The second is MuonClip, and this is what truly sets Kimi apart from everything else. It extends the Muon optimizer by adding something called QK-Clip. For each attention head, it monitors the maximum pre-softmax logit during training, and if that value exceeds a threshold of around 100, it immediately rescales the query and keyweight matrices on the fly. The result is the smoothest training loss curve anyone has ever published at this scale. They trained across 15.5 trillion tokens and recorded 0 instability events, not a single loss spike across the entire run. Compare that to standard AdamW training, where a single spike can cost weeks of compute and millions of dollars in wasted resources. MuonClip simply doesn't spike, and that turned a multi-million-dollar gamble into a predictable process. So that's the language backbone. But Kimi K2.5 isn't just a language model, it also sees. And how it handles vision matters a lot. The vision encoder is called MoonVit 3D, and it's initialized from SwiGLU SO400M. The key design choice is that it processes images at their native resolution. There's no resizing, no squishing a high-resolution photograph into a tiny 224 by 224 grid. Instead, they use a technique called NaVit packing, which handles variable resolutions by fitting patches together like Tetris pieces. So there's no wasted padding, and every pixel contributes useful information. Images flow from MoonVit through a 2-layer feed-forward projector that maps vision features directly into the language model's embedding space. Everything is native multimodal from the ground up, not bolted on after the fact. For video, they take 4 consecutive frames, run them through the exact same MoonVit encoder with complete weight sharing, and then temporally average the patch features across those frames. This means you can process 4 times as much video content in the same context window. Native resolution preserves the fine-grained detail, temporal averaging handles the motion, and one unified encoder handles both images and video without any special case logic. This is where the paper gets genuinely counterintuitive, because this result broke what most researchers in the field assumed was true. The question is simple. When do you mix vision and text data during pre-training? The obvious answer, the one that everyone assumed was correct, is that you train mostly on text first to build a strong language foundation, and then ramp up the vision data later. More vision data later should mean better vision performance, right? Wrong. They tested both approaches directly. Early fusion means mixing 10% vision with 90% text from the very first training step, keeping that ratio constant across all 15 trillion tokens. Late fusion means starting text heavy and then gradually ramping up to 50% vision data later in training. Early fusion destroyed late fusion on every single benchmark they tested. MMMU Pro hit 78.5 versus 73.2. OCR Bench reached 92.3 versus 87.1. Video MMMU scored 86.6 versus 80.4. Less vision data used earlier produced strictly better results across the board. The lesson is that timing matters more than quantity. A small, consistent amount of vision data from the very beginning creates deep cross-modal alignment in the weights that you simply cannot replicate by bolting vision on after the fact. Late fusion is like grafting a branch onto a tree, but early fusion is like growing them together from the seed. And growing together wins every time. This next finding made me reread the paper 3 times because it sounds like it shouldn't be possible. Text-only fine-tuning improves the model's vision performance. Just let that sink in for a second. After pre-training with early fusion across 15 trillion tokens, Kimi K2.5 has deep vision text alignment baked into every layer of its weights. The representations for vision and language are entangled in a productive way. So, when you fine-tune on text-only tasks, teaching the model better reasoning and better instruction following, you're actually upgrading the shared reasoning engine that both modalities rely on. Because vision runs on that exact same engine, vision performance goes up for free without seeing a single image during fine-tuning. Text tasks improve, vision tasks improve, and the model saw zero vision training data during that phase. But here's where it gets even stranger. When they added carefully designed vision examples to the fine-tuning data, handcrafted step-by-step visual reasoning trajectories built by researchers, the model's vision accuracy actually went down. Text-only fine-tuning made vision better. Adding explicit vision examples made vision worse. The explanation is that the model had already figured out visual reasoning on its own during joint pre-training. The hand-designed examples didn't help because they taught a narrower reasoning strategy than what the model had discovered by itself. Sometimes, the best thing you can do for a model is simply get out of its way. Just when you think the cross-modal surprises are over, there's one more that ties everything together. They applied reinforcement learning specifically to vision tasks, rewarding the model for getting visual questions right and penalizing wrong answers. Standard RL fine-tuning. But then they checked the text benchmarks, and the text scores went up. MMLU Pro, which is a pure text benchmark, jumped from 84.7 to 86.4, a gain of 1.7 from training exclusively on vision. GPQ-A Diamond went from 84.3 to 86.4, up 2.1. Longbench V2 improved by 2.2%. Text benchmarks getting better because you trained on vision tasks. The reason this works is that their RL training is organized by ability rather than by modality. Knowledge, reasoning, coding, and agentic tasks each have their own training domain, and vision and text examples train together within each domain. When the model learns precise spatial reasoning from vision RL, that precision transfers directly to logical reasoning, mathematical reasoning, and everything else that shares the same underlying skill. This is genuine bidirectional enhancement, where the whole truly becomes greater than the sum of its parts. Everything we've covered so far sounds incredible, but there's a very practical problem lurking underneath all of it. Training a trillion parameter model on this much data is stupidly expensive. We're talking millions of dollars per training run. Toggle is their answer to this problem, and it's elegantly simple. During reinforcement learning, they alternate between two phases. In the first phase, budget mode, they cap how many tokens the model is allowed to generate for each response. You have to solve this problem, but you only get this many tokens to do it. This forces the model to cut out redundant verification steps, mechanical recalculations, and verbose filler. It learns to be efficient because it has no other choice. In the second phase, the model gets full capacity with no token limits at all. They alternate back and forth. This is where things get really interesting, because everything up to this point has been about the model itself. But Kimi K2.5 isn't just a model, it's an agent, and they completely refought how AI agents should work. Traditional agentic AI operates sequentially. The agent thinks, takes an action, observes the result, thinks again, takes another action. Step A leads to step B, leads to step C, leads to step D. 4 steps chained one after another, and you have to wait for each one to finish before the next one can start. It works, but it's painfully slow. Agent Swarm flips this entire approach on its head. An orchestrator sits at the top, functioning like a project manager. It looks at the incoming task, figures out which parts are independent of each other, and fans them out to specialized sub-agents that run in parallel. Those same 4 tasks now have a critical path of just 2 steps: the orchestrator's planning decision plus the runtime of the longest sub-agent. In practice, this delivers a 4.5x speedup. And that's not a theoretical number, that's measured. The training framework behind this is called PARL, which stands for Parallel Agent Reinforcement Learning. The clever design is that only the orchestrator is trainable, while the sub-agents are frozen checkpoints. This decoupling solves the credit assignment problem and eliminates the training instability you'd get from trying to train. Let's talk actual numbers, because claims are cheap and benchmarks are what matters. On reasoning tasks, Kimi K2.5 scores 96.1% on AIM 2025 and 87.6% on GPQ-A Diamond. On coding, it hits 76.8% on SWE Bench and 85% on Live Code Bench. These aren't just competitive scores, these are frontier-level results coming from a fully open-source model. On Vision, MMMU Pro reaches 78.5, OCR Bench hits 92.3, and Video MMMU scores 86.6. On Agentic tasks, BrowseComp lands at 74.9, OS World at 63.3, and on Humanity's Last Exam, it scores 50.2%. That makes it the first open-source model that's genuinely competitive with proprietary systems on what's considered the hardest benchmark in AI right now. But benchmarks are just a snapshot. Of course, performance without affordability is just a benchmark trophy that sits on a shelf. So let's talk about what this actually costs to use. Claude Opus 4.5 runs about $200 a month. GPT 5.2 is around $160. Kimi K2.5 through Moonshot's API costs just $30 a month, which is 76% cheaper for performance that's in the same tier. If you want to run it yourself, the full FP16 model is over 500 GB, so that's not happening on consumer hardware. But INT4 quantization brings it down to 245 GB, while retaining 85% of the original performance and doubling inference speed. You can deploy it through frameworks like VLLM, SGLang, or K-transformers. And 2M3 Ultra Max connected together can give you about 15 tokens per second, which is usable for real workloads. The bottom line is that you're getting roughly 90% of Claude Opus capability at 7 times lower cost, with fully open weights and open code under a modified MIT license. For the vast majority of use cases, this is the obvious choice. Let's step back and look at the full picture, because one paper just delivered 6 breakthrough techniques, and each one is impressive on its own, but together they tell a much bigger story. They took the same architecture as DeepSeek V3 and used MuonClip to deliver zero-loss spikes across 15 trillion tokens of training. MoonV3D brings native resolution vision without any compromises. Early Fusion proved that less vision data used from the start beats more vision data added later. Zero Vision SFT showed that text-only training can improve vision performance. Joint Multimodal RL revealed genuine bidirectional enhancement between modalities. And Agent Swarm runs 4.5 times faster through the PARL framework. 1.04 trillion parameters, 32 billion active, fully open weights on Hugging Face under a modified MIT license. The race to AGI isn't going to be won by whoever locks down the most powerful model behind the paywall. It's going to be won by whoever shares the most powerful techniques with the world. And with this paper, Moonshot AI just shared everything. If this video changed how you think about open source AI, hit the like button. Subscribe if you want more deep dives like this one. Drop a comment and tell me which finding surprised you the most. Was it the early fusion result, the zero vision SFT paradox, or Agent Swarm? The paper and model weights are both linked in the description. Now go build something with it.